Hi everyone, welcome to this introductory video on transport phenomena, a core subject in chemical engineering that you're about to dive into for the first time. I'm here to walk you through the syllabus and give you a clear picture of what this course is all about, what you'll learn, and how it will help you as future engineers. Let's get started by breaking down the syllabus step by step. In Unit 1, we will be studying similarity between heat, momentum, and mass transport, molecular and convective transport, definition of transport properties, viscosity, thermal conductivity, diffusivity, Newton's law of viscosity, Fourier's law of heat conduction, Fick's first law of diffusion, dimensionless numbers in molecular transport, convective transport, and total flux. In Unit 2 of Transport Phenomena, we will be studying interface transport, transport coefficient, physical interpretation of friction factor, heat transfer coefficient, mass transfer coefficient, dimensionless number in interface transport, various transport analogies, the Raynaud analogy, the Chilton-Colburn analogy, evaluation of transfer coefficient, engineering correlations. Now in Unit 3 of Transport Phenomena, we are going to study about shell momentum balances, velocity distribution in laminar flow, shell momentum balances, and boundary condition. Different cases for discussing shell momentum approach like flow of falling film, flow through a circular tube, flow through an annulus, flow of two adjacent immiscible fluids. In Unit 4, we will be covering topics like shell energy balances and temperature distributions in solids and laminar flow, shell energy balances, boundary conditions. Different cases for discussing shell energy balance approach like heat conduction with an electrical heat source, heat conduction with a nuclear heat source, heat conduction with a viscous heat source, heat conduction with a chemical heat source, heat conduction through composite walls, heat conduction in a cooling fin. In Unit 5, we have shell mass balance for concentration distributions in solids and laminar flow, shell mass balances, boundary conditions, diffusion through a stagnant gas fill, diffusion with a heterogeneous chemical reaction, diffusion into a falling liquid fill, gas absorption, diffusion into a falling liquid fill, solid dissolution, diffusion and chemical reaction inside a porous catalyst, diffusion in a three-component gas system. In Unit 6, we have the equations of change for isothermal systems, the equation of continuity, the equation of motion, the equation of mechanical energy, the equation of angular momentum, the equations of change in terms of the substantial derivative, use of the equations of change to solve flow, steady flow in a long circular pipe, falling film with variable viscosity, operation of a Couette viscometer, shape of the surface of a rotating liquid, flow near a slowly rotating sphere, and more.
Are you ready to break down Unit 1 of a transport phenomena? I know it sounds heavy, but we'll make it fun.
Absolutely, Swish. So, transport phenomena, it's basically about how heat, fluids, and particles move from one place to another, like boiling water on the stove. Heat moves through the pot to heat the water, right?
Exactly. And there are three main types of transport: heat, momentum, and mass transport. Think about sunlight warming your skin, water flowing in a pipe, and sugar dissolving in a tea.
Right. And transport can happen in two main ways. First, molecular transport. It's like when you spray perfume, it spreads out naturally. That's molecule moving around.
And the second is convective transport, like when a fan spreads cool air around a room, the air moving and carrying heat or particle with it. Simple, right?
Yes. Now, let's talk about some important properties. Viscosity, for example, it's like how thick or sticky a fluid is. Honey has high viscosity, it flows slowly, unlike water.
Exactly. And then there are thermal conductivity. It's about how well something conducts heat, like how well metal heats up quickly but wood doesn't.
Oh, and diffusivity, it's how fast particles spread. Like when you drop food coloring in water, it's spread all over. It's kind of beautiful to watch, honestly.
Totally. And now let's cover some important laws. First, Newton's law of viscosity. It explains the force needed to move a fluid, like pushing honey versus water. Honey is tough.
And Fourier's law of heat conduction. It's about heat moving from hot to cold. Like when a metal spoon heats up in a hot soup. Simple but super important.
Yup. And there's Fick's first law of diffusion. It says particle move from higher concentration to lower concentration. For example, sugar dissolving faster when you stir it. Sweet, right?
Nice one, Swish. Now let's talk about dimensionless numbers. Engineers use them to compare systems like Reynolds number for fluid flow and Prandtl number for heat transfer.
Exactly, and there's a total flux. It's the rate at which something transfers over an area, like how much heat passes through a wall over time. Super useful in a word problems.
So basically, Unit 1 help us understand how heat, particles and fluids move. And when we understand that, we can solve real problems. Designing cooling system, predicting air pollution, so many applications.
Yeah, that's it for Unit 1. Not so bad, right? Next, we'll dive into Unit 2 and explore interface, transport, and transport coefficients.
Sounds good. Moving ahead, we are going to discuss what unit number 2 have for us to unveil and learn to become a good engineers. After all, unit 1 was fun exploration.
Right.
Let us start
Let's jump into
discussing
Unit 2 of
now.
transport phenomena. This one is all about interface transport and transport coefficient. Sounds tricky, right?
Yep, and it's super important to understand how these transports happen across different phases, like steam condensing on a cold surface or moisture evaporating from cloths drying in the sun.
So, interface transport is all about transfer of heat, mass, or momentum between different phases, like air and water or solid and a gas. For example, evaporating water from a pond.
Right, and the physical interpretation of a friction factor is another key concept. It's all about how roughness and velocity affect fluid flow. More friction means less efficient transport.
And then we have transport coefficients. These are like efficiency rating for how well heat, mass, or momentum move between phases. Higher coefficient mean faster transport.
And just like with heat transfer, we have correlation to estimate transfer coefficients. Engineers use these formula to simplify real world problems.
Heat transfer coefficient is a big one. It measures how effectively heat moves between a surface and a fluid, like cooling hot metal with air or water.
Exactly, and using dimensionless numbers makes it so much easier to compare different systems. Like how engineers use Reynolds number to predict if fluid flow is smooth or turbulent.
Now, let's talk about the mass transfer coefficient. It measures how quickly particle or a molecule transfer between phases. Think about dissolving salt in water or oxygen moving from air to blood.
And about analogies, they are like shortcuts. By understanding one type of transport, you can predict others, like how airflow affects heat transfer in air conditioners.
Dimensionless numbers are back in interface transport. They help simplify complex problems. Things like Nusselt number for heat transfer or Sherwood number for mass transfer.
And the Chilton-Colburn analogy is super handy. It links heat, mass, and momentum transfer using dimensionless number. So useful in designing heat exchanger or chemical reactors.
And we also have analogies like Reynolds analogy, which connects heat, mass, and momentum transfer. It's like finding similarity between different type of transport.
So, Unit 2 is really about making sense of how heat, mass, and momentum between different phases and using analogies and correlations to make predictions.
Lastly, we have Chilton-Colburn analogy. It's modified version of the Reynolds analogy. Engineers use it to estimate heat and mass transfer more accurately.
That's a wrap. I think we made Unit 2 sound way simpler than it actually is.
We are
Ready to
now
move
on
on the next
Unit
part?
3. This one is all about steady state transport in laminar flow. Sounds fancy, right?
Definitely. So, steady state means things are not changing with time, like when water flows smoothly through a straight pipe at a constant rate. No surprises.
Exactly, and laminar flow is when fluid moves in smooth layers without mixing, like honey pouring from a spoon. Slow, smooth, and orderly.
And when we study these flows, we use something called shell balance method. It's way to break down complex system into tiny layers to understand how heat, mass or momentum moves.
Right, and for fluids, we use momentum balance equation. It helps us find velocity profile in a pipe or channels. Think of water flowing through a pipe, faster in the middle, slower near the edges.
And similarly, for heat transfer, we have the energy balance equation. It's used to find temperature distribution, like how heat separates through a metal rod when one end is heated.
Exactly, and for mass transfer, we use the mass balance equation. It helps us figure out how particles spread or dissolve, like sugar diffusing in a water.
And it's cool because once we set up these equations, we can solve them using boundary conditions, like the temperature at the surface of a hot plate or the concentration at the membrane.
Oh, and we also use velocity profiles for solving these equations, like the parabolic profile you get when fluid flows steadily through a pipe.
And for heat transfer, we use temperature profiles, like how temperature gradually changes from a hot surface to a surrounding air.
Same goes for mass transfer. We create concentration profiles to see how particles move from high concentration to low concentration.
And it all comes down to understanding how these profiles change with distance. That's why we use equations and boundary conditions to get accurate results.
Yeah, and when conditions are steady, things get simpler. Like once we reach a steady state, the profile don't change with time, makes calculation way easier.
Exactly. And these concepts are super useful in designing things like heat exchangers, pipe, and reactor, where we want smooth, controlled flow.
Alright, so unit 3 is all about understanding steady flow and solving them using balance equation and profiles. Ready to tackle the next part? It's time for
Absolutely.
unit 4.
Let's keep
This one
digging
is
in.
all about unsteady state transport. Unlike steady state, things here change with time.
Exactly, like when you put a hot metal rod in a cold water, the temperature of a rod changes over time until it cools down completely. That's unsteady state heat transfer.
Right. And it applies to momentum and mass transfer too. For example, imagine a perfume bottle just sprayed in a room. The concentration of particles is spread over time.
And it's similar with momentum transfer. Like when you suddenly stop stirring a liquid, the motion gradually dies down instead of stopping instantly.
To analyze unsteady state processes, we use differential equations with the time as a variable. That's where things get a bit more complex.
Yeah, and solving these equations usually involves initial conditions. Like what's the starting temperature, concentration, or velocity before things start changing.
And just like in a steady state, we still use boundary conditions, but here they can change over time. It's like constantly adjusting the heat on a stove while cooking.
And the solutions to these equations give us profiles that change with time, like how temperatures in a metal rod gradually cools from hot to room temperature.
Oh, and don't forget about the lumped system analysis. It's simpler approach where we assume temperature or concentration is uniform throughout a body.
Exactly. That's super useful when the resistance to heat or mass transfer is low, like heating a small metal sphere quickly in boiling water.
And when things aren't uniform, we use distributed system approach. That's when we have to consider changes at different points within a system.
Right? And solving those can be tough, but we often use numerical methods or software to get accurate results for complicated problems.
And unsteady state transport is everywhere. Think about cooling hot food, drying wet clothes, or even charging batteries all involve changes with the time.
And it's essential for designing systems where conditions change rapidly, like reactors, air conditioner, or even cooking appliances.
So, Unit 4 is about understanding how transport processes evolve over time and using equations to predict those changes.
Yep, and now we're ready to move on to the
Alright,
next part.
here
Let's
we
see
are
the road.
at Unit 5 Turbulent Flow. This one is all about chaotic, unpredictable motion. Way different from laminar flow.
Yep, unlike laminar flow, turbulent flows is all over the place. Like a smoke from a chimney or water rushing through a river. It's messy but super important to understand.
Exactly, and it's not just random. Turbulent flow has pattern and structures called eddies, like swirling whirlpools of different sizes.
And when we study turbulent flow, we break it down into mean flow and fluctuations. The mean flow is the average motion and the fluctuations are the chaotic parts on top of it.
We use something called Reynolds average Navier-Stokes equation to deal with the turbulence. It helps us focus on the mean flow while considering the effects of fluctuation.
And to simplify things even more, we use turbulence models. They are like shortcuts to predict how turbulent flows will behave without solving every tiny details.
And then there's the K omega model. It's better at understanding flows near solid surfaces like air flowing over a plane wings or fluid moving through a pipe.
And another model is a K epsilon model. It focuses on predicting the turbulent kinetic energy and how quickly it dissipates. Super useful in engineering applications.
And speaking of pipe, turbulent flow is really common in industrial systems like oil pipelines, HVAC systems, or even blood flow in large arteries.
And that's why understanding turbulence is so important. It helps us design more efficient systems, reduce energy losses, and even predict weather patterns.
And we can't forget about dimensionless numbers again. The Reynolds number helps us figure out if a flow is laminar or turbulent. Higher number usually means turbulence.
And the Prandtl number and a Schmidt number are also useful for predicting how heat and mass transfer behave in turbulent flows.
Oh, and we also use something called the mixing length theory. It's way to estimate how far fluid particles move before they mix with the surrounding flow.
And turbulence enhances mixing, which can be good or bad. Good for things like mixing chemical quickly, but bad when it causes energy loss at pipelines.
So Unit 5 is really about understanding how turbulence works, predicting it using models and applying it to a real world systems.
Yay, and it's such a huge part of
We had
engineering.
made to Unit
Now
6
let's move to
boundary
the
layer
another.
theory. This is where things get interesting, especially for the fluid flow over surfaces.
Definitely. So the boundary layer is the thin region near a solid surface where fluid flow is affected by friction, like air moving over a car's surface.
Exactly, and while this layer, the velocity of the fluid changes from zero at a surface to the free stream velocity away from it. It's like a smooth transition from slow to fast.
And the change in velocity creates a velocity gradient, which is super important for understanding shear stress and heat transfer near surfaces.
And the boundary layer can be either laminar or turbulent. Laminar when the fluid moves smoothly, and turbulent when it is chaotic.
And the transition from laminar to turbulent flow usually depends on the Reynolds number. Higher Reynolds number generally mean turbulence.
And we use the boundary layer equations to analyze fluid flow near surfaces. These equations simplify the Navier-Stokes equation by focusing on the thin region near the surfaces.
Exactly, and solving these equations help us predict things like drag force on vehicle or heat transfer rates in heat exchange.
And speaking of heat transfer, there's also a thermal boundary layer. It's where temperature changes from the surface temperature to the fluid temperature.
And when we have mass transfer, there is a concentration boundary layer. It shows how particles or molecules spread from a surface into the fluid.
And just like with velocity, these boundary layers can be laminar or turbulent, and the thickness of the boundary layer changes depending on the flow and the surface condition.
And engineers often try to control or reduce boundary layers to improve efficiency, like designing airplane wings to minimize drag or using fins to enhance heat transfer.
Oh, and don't forget about the Balacious solution. It's a famous solution for predicting laminar boundary layer profiles over a flat plate. Simple but really powerful.
And for turbulent boundary layers, we usually rely on empirical correlations and models since the math gets way too complex to solve directly.
So, Unit 6 is really about understanding how fluid, heat, or particle interact with surfaces and predicting those interactions using boundary layer concept.
Yep, and it's so important for designing things like airplanes, ships, heat exchanger, and even chemical reactors. On to the next one. So the objective was that student will be able to develop and use velocity profile, flux profile, model equations for different systems in heat, mass and momentum transfer using shell balance approach. And there are some outcomes. First, correlate the heat, mass and momentum transfer. Explain the shell balance approach and boundary conditions. Obtain velocity, concentration and temperature profile, heat, mass and momentum flux profile and other important equation. Solve design problem using profile equations. There are some books that can be referred to study transport phenomena. First is Momentum, Heat and Mass Transfer by Bennett, CO and J. Myers. Second, Transport Phenomena, a Unified Approach by Brodkey, Robert S. and Hershey, Harry C. Third, Transport Process and Separation Process Principle by Giancopoulos, C.J. And fourth, Modeling in Transport Phenomena by Ismail Toshun.